Hi, everyone. My name is Xiaoxi Chen. If you're on GitHub, my handle is Pessimistress. I've been working on deck.gl since 2016, and I'm currently the chair of the technical steering committee of VizGL. Just to open for the day, I would like to take you through the history of the project and what's currently on our mind. deck.gl started as an internal project at Uber. At the time, Uber was growing exponentially, and we're already having hundreds of thousands of trips per day in one city. And the company was desperately looking for a tool that can help them manage all the trips that's currently going on in the street, and also look back and do analytics on how the platform performed and how they can improve it. The issue is it was not very easy at the time. I think the very first web tool that they built was using D3 and SVG. If you've been there, you know what happens after you have, say, more than a few thousand elements on screen. It gets very choppy and not very responsive. And it just gets worse and worse because every time you update the position of something or the styling, it just locks up the entire thread. And just DOM layout and re-render is very expensive. Uber put together a visualization team and took a step back and look at the problem. We'll think about it this way: data, as in numbers in the table, we want to convert that into pixels, and there is some function that does the transform from number to visual properties, and this is something that we can do very easily in parallel, and that is exactly what GPU is very good for. You know, we have many pipes, and each pipe may not be as powerful as a CPU core, but you can do thousands and tens of thousands of in parallel at the same time, and that ended up being extremely performant and responsive, and that was what we went for. This is one of the demos on our website. I don't know. Animation doesn't work so well. Yes. This particular one looks at almost 1 million points in New York City, and what we're doing is we are converting the lat long and some visual properties of the point, each data point, into maps to a circle and screen pixel position on screen. And every time you pan and zoom with your mouse, all we are sending from the CPU is just the updated transformation matrices to the GPU, and the GPU is doing all the heavy lifting of rendering that shape and finding out what position it should be on screen. And this ends up really smooth, and we can easily go to 60 frames per second. Yeah, this is another example, what we call brushing. When you move the mouse, we are only showing the connections that starts or ends from that region that's under your pointer. Again, every time you do so, we're not doing the filtering on CPU. We're only sending the updated position to the GPU, and the GPU is figuring out what to draw and what not. This is the screen grid layer where we are doing aggregation on the GPU. So every time you change the viewport, it is recounting. It divides the screen into a few hundred bins, and every time you change the viewport, it's recounting how many data points falls into each bin. Doing it on GPU, we can get to a reasonable frame rate, something like 20 or 30 with this data set, and that is just unthinkable if you do so on the CPU. We originally open sourced deck.gl in 2016. I think the first relatively mature version was V4. That was published in 2017. And we did a big push on it. The adoption was slow but steady. Today we have, I think I have a graph later, we have just over 100K downloads per week. And we know a lot of commercial products that are built on top of this. And this has truly grown beyond what we had in mind when we were just a team in Uber. In V4, that was the origin of some of the foundation layers that we are known for today. And V5, we really went in to test what other stuff we can offload to the GPU. Things like auto highlight, where you move your cursor and we highlight the feature that's being picked. This is all done on the GPU. Attribute transition, where we can smoothly go from one location or color or size to another. This is based on WebGL 2. And as of this year, all major platforms and browsers are supporting this. In V5, we also did a big push to support non-React scenarios. I don't know how many of you were deck.gl users at the time. Initially, deck.gl was a React-only component, and that was a big barrier to adoption for a lot of, especially non-JavaScript developers. Since V5, we have been doing a big push to bring deck.gl closer to whatever platform that people are developing on. In V6, a big improvement that's under the hood was the 32-bit high precision projection. We'll see later that deck.gl made a conscious technical decision that we are doing the web marketer projection on the GPU, not the CPU. And the problem with the GLSL shader is it only supports 32-bit float. And if you translate that to degrees in longitude and latitude, that is about 1 meter precision. And if you zoom to street level, you will clearly see things start jittering. Originally, deck.gl handled this by implementing its own 64-bit matrix calculations in shaders. So that is a gigantic shader that we're including in every layer, and we're sending basically every double number in 2 parts, high part and low part, and we're collating them in the shader. It is very heavy calculation, and that shader had a lot of compilation issues. And in V6, we switched to an offset strategy. When you zoom in far enough, we will, instead of using the full double value, we switch to using the difference between that and the center of the viewport, and that greatly simplified the calculation and the shader code. We also did a big push on GPU aggregation, and V6 was the first time we collaborated with a major base map provider. That was Mapbox custom layer API. And we did the Mapbox layer that can interleave with the Mapbox bound text, so you can have correct occlusion with all the 3D buildings. In V7, we introduced tile layer and tile 3D layer. That ended up being a major theme of development up till today. Introducing tiles enabled us to render things that is larger than you can hold in the browser's memory. And now you can literally render data sets of billions of data points and also amazing detail. Right now, tile 3 layer supports Hi3S, supports 3D tiles, and we have more OGC formats that's in the pipeline that's coming. We also introduced a new effect system, so we have proper lighting and shadows and post-processing. And V7 was when we did a big push on binary data support, so you don't have to convert everything into a JavaScript array. A big thing in V7 was we introduced loaders.gl, that is an library agnostic parser library that you can use to go from any popular geospatial or 3D format into something that can be directly used in WebGL rendering. It has been thriving as its own independent project, but a very nice companion to deck.gl. V8 is where we currently are. We did a big push on performance improvements, so we dropped a lot of legacy code that was dragging us down. We introduced MVT layer that supports the Mapbox vector tiles format. That has been a big thing. We also started experimenting with non-web marketer projections such as glow mode and other nice features, including the GPU-based masking feature that allows you to only show data that's within a geofence. If you haven't played with it, it's pretty cool. So we have, right now we have a big official layered catalog. We also know of a bunch of third-party layers that are open sourced and easy for people to plug in and use. It allows, especially like new developers to quickly make things work, plug in their data, and see things work out of the box. And that has been huge for our adoption. I want to just show a little bit of the where we are comparing to some of the other libraries that's often being compared with deck.gl. So if you think of a typical geospatial visualization process, we have data that's in the world space, typically say longitude, latitude in degrees and altitude in meters. And we do the pre-projection where we convert this nonlinear coordinate system to web marketer, which is an Cartesian system that is uniform on all three axes. And from there, we will do styling, including calculating the size. If you have a path, we will need to extrude it and calculate the corners. And if you have like icons or text, we have other processing. And then we project that from the common space, that's the Cartesian space, to screen. That is the clip space. If you look at WebGL libraries such as ReGL or 3JS, because they are not visualization specific, they do not really handle things like marketer projection or styling, but they do the last part pretty good. They are more suitable for doing like a 3D game sort of scenario. Where you can easily play with textures and models, but because 3JS uses a SceneGraph data model, when you have millions or even more data points, it's a lot of draw costs, and it quickly breaks down. If you look at vector web maps, or say comparing to Mapbox, you are doing pre-projection on the back end. So when you generate the tiles, you are already converting them to the web marketer space. And you can do some dynamic styling in the front end. That's done on the CPU. That choice is because CPU can do it very nicely. You have a very nice like label layout. You have very nice corners of your paths. But because it's a static map, most likely you are only doing it once. And once you pay that price of that overhead, each tile always look the same, and the projection can be handled on the GPU as you move and pan around. If you look at deck.gl, it's completely different. We send all the data in their world space coordinates directly to the GPU. We're not doing anything on the CPU. The GPU does the Mercator projection. The GPU calculates the offset and corners of stuff. We made this decision specifically because we're handling a large amount of data that possibly changes very frequently. And as you can see in some of the follow-up use cases, it is very important for us to move things as fast as possible through that CPU to GPU pipeline. And we don't want to spend any, we don't want to waste any time on the CPU. This was one of the products we were building with deck.gl at Uber and was later open sourced as avs.auto. This is visualization of a self-driving car moving in the street. And we have over 100 layers in this scene where you have data coming in different coordinate systems. Almost all layers come in different coordinate systems. There are stuff that's relative to the street. There's stuff that's relative to the car that is changing every 10th of a second. And you have stuff that's coming from the camera. And all of these are collated together very nicely with deck.gl. Kepler.gl, I think this is probably the most well-known projects that's built on top of deck.gl. Also won an Information is Beautiful award, I think in 2019. And I believe a handful of companies are building their own offering on top of it. It offers a no-code sort of scenario for people to analyze their data. There was another open source project at Uber that looks at machine learning models, and a lot of these are custom layers that's written in deck.gl, so they can handle a large amount of input data and a large amount of subgraphs on the screen. I grabbed this stats last night. We are currently at 100K downloads per week, and I'm just listing some of the notable companies that have been contributing or sponsored the project throughout this process. And we have a fast-growing community that is not just hacking around on their own, but also building their commercial products, their consumer-facing products that is on top of deck.gl. And we're committed to help them get this, keep this rolling. If you look at NPM packages with the keyword data visualization, there are over 1,000 of them. Anyone can publish a package. The real trick is how do we get people to use ours, and how do we get people to contribute to ours, because that's the most valuable thing is the contributor's time. For us, we are not trying to be the go-to package for everything. We're not trying to compete with 3JS. We're not trying to go into the 3D gaming space. And we're not even trying to compete with base map providers where they know their data best and they know how to render them for the static use cases. For us, since the start, deck.gl has been this battle-tested, highly performant solution for very large dynamic data, and has a developer focus, as in we are well documented, and you can see how things are implemented from top to bottom, and every step of the way, the API exposed ways for you to write your own thing. We have views, we have different projections, we have different layers, and all these things are exported and documented, so you can write your own instead of using something that's already in the library. and that has always been very important to us, that developer experience. Also, deck.gl want to keep platform agnostic or platform neutral, where we are not locked into one particular solution or one particular data format. You can use it with React. You can use it with any base map provider, and you can use it with any data format of your choice. And it's all very transparent how things work. It's not, we are not trying to develop a black box there. Also, another side of that competition is we understand that it's not all technical. A lot of the experience come from what do people see when they're trying to start using this project. What kind of help can they get? What kind of examples can they get? We're currently in the process of revamping the website. We have some design help to redesign how things are laid out and how information can be found in our documentation. Also, we spend a lot of time on GitHub engaging with the community when have questions or suggestions. And we try to be as transparent as possible. All our developer docs are on GitHub as well, outlining our roadmap and what's in the backlog. One big thing that happened to VizGL in the last 2 years was in 2020, we moved to open governance. So we are no longer under Uber's organization. We initially moved into the Urban Computing Foundation, which was its own organization, and then that got merged into OpenJS Foundation. If you don't know, OpenJS Foundation is the subsidiary of Linux Foundation that is home to things like Webpack, Node.js, and ESLint, and all the big names that have 100 times the user that we do. But also they have those resources and they have a good understanding of how to build a community, and they're helping us shaping our organization and how we run things, and that's how we are all here today. For me personally, I currently work at Microsoft. My day job is not maintaining this library anymore. Like when back at Uber, for me that decision was that was a conscious decision, because I want to be positioned in the technical steering committee where I'm neutral and I don't have too much invested interest in the direction of the packages. My own personal mission is to help more contributors get on board and help more people understanding the code base and grow to understand WebGL and how this whole thing works, and find where they can create value. And another big thing that's on my mind personally is how we can get more companies to have vested interest in this project, so they are willing to invest money and their developer time to keep this project sustainable and growing. As you will see later today from all the talks, we have a great profile of sponsors that currently very interested in being compatible with deck.gl and making the changes that will work better with this open source community. And we also have a handful of companies that have even started their business around the concept of providing good visualization or user experience around visualization. And they embrace this open core concept where their core code base is out in the open and everyone can use with a permissive license. And their business is adding some additional value on top of that open source project. I don't know, how well that will work for everyone. But from my perspective, I'm all supportive, and I'm all in supporting them making this experiment. And I hope we have more business models and more successful stories coming out of this, because that is what's going to keep us sustainable and growing.